In this topic, we'll do several lecture segments to analyze the assembly code generated from the program shown here in the diagram, primes.c. This is a larger program than any we've analyzed, and it makes heavy use of bitwise operations. And those are assembly instructions that operate on register contents as patterns of bits, not binary numbers. Primes.c examines the numbers from 0 to 319 to determine which are prime, and it records prime or non-prime status for each of those 320 different numbers using an array prime set of just 10 32-bit ints. See it declared right here, for instance. Now, how it does so is the main point of the program. Primes.c uses 1 bit per number, setting the bit to 0 if the number is non-prime and to 1 if the number is prime. Each 32-bit int in primeset thus stores primeness information for 32 values. Primeset zeros bits, with the red arrow there, indicate primeness for the values 0 through 31. And importantly, that's with the LSB on the right indicating primeness for 0, and the MSB indicating primeness for 31. Since 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31 are prime, this means primeset 0 will look like the diagram does when the program is done. So stop for a moment and be sure you understand how the bit pattern in that number 0 element corresponds with a list of prime values in the range 0 to 31. I'll even make that a brief review here in the lecture without any kind of an in-lecture question. That's the primeness for 0, for 1. 2, however, the third bit in, is prime, and so is 3, the fourth bit in. If we get over to the fifth bit, that's the bit for 4. 0, 1, 2, 3, 4, and that's not prime. But the one for 5 is, 6, no, 7, yes, 8, 9, 10, 11, yes, 12, 13, yes. You get the pattern. So, a question then for you, an in-lecture question. What index of primeset, understanding of course that these other indexes contain yet more values for more prime numbers, in particular the remaining elements store primeness for the values 31 through 319. And there's a grand total of 320 bits in primeset. So, with that in mind, which index of primeset has the bit for the value 119? How in general do we compute which index of primeset to use given a value v? Check your rule against 319, which should yield index 9, the last one in the array of course, and 31, which as we already know should yield index 0. And then the answer here is that index 3 would contain the bit for 119, and in general the value divided by 32 gives the correct index. Okay, so now how do we choose which bit within that element represents a given value? Let's start by numbering the bits within each element from 0 for the LSB up to 31 for the MSB. This right to left numbering from least to most significant instead of the reverse might seem a little odd, but it turns out to be convenient to number bits this way within an int. For instance, note that each bit is numbered according to the power of 2 that is its place value. The LSB has place value 2 to the 0th power, and the MSB has place value 2 to the 31st power. Given this numbering system, we can see that the values 0 through 31 are represented by bits 0 through 31 in that first element, primeset bracket 0. In primeset 1, the values are 32 through 63, and so on. Question 2. What simple computation will give us the right bit number given a value v, the right bit number within whatever index is appropriate? Check your rule against 0, which should of course give you bit number 0, and 319, which back in the farthest index 9 out there should give you bit number 31. And the right computation turns out to be the value modulo 32. The remainder, when dividing the value by 32, is the right bit number. Concretely, if I have bit number 0, well then 0% 32 is 0. And by contrast, if we're looking for the bit for value 67. The modulo there would be 3, and it would be bit number 3 in index 1. Okay, now let's look at the setBit function, which is down at the end of primes.c over here. The setBit function uses the two equations just discussed to pick out an individual bit in prime set and set it to 1. It takes several steps to do this, and it's important to understand them before we look at their assembly translation. Parameter prime gives the number of the bit to set from 0 to 319. And then, of course, prime set is passed in as an array or array reference. The set bit then picks the right index of prime set and uses bitwise operations to set just one bit in that element to 1 without changing the others. The right index, per our discussion above, is prime divided by bits per int. And bits per int, of course, is a constant above set to 32. And the right bit number is prime percent bits per int, like over here. So this C expression right here deserves some attention. This performs a left shift, an operation we discussed in a prior lecture. It shifts the bits of the first operand, which is simply 1, to the left by as many positions as indicated by the second operand, the value prime modulo bits per int. Any pair of integer operands is allowed for this. The 32-bit pattern for 1 is all zeros and a 1. Thus, if we were to shift it left by, for instance, 21 positions, then we would have a value hope that's 21 zeros. You get the picture, and it would look about like that approximately. Now, C also has a right shift operator, and we'll use it later in the discussion, and it performs either an arithmetic right shift or a logical right shift. Again, recall the distinction from prior lecture, depending on whether the integer operands are declared signed or unsigned. The left shifted 1 is the second operand. This guy right here is the second operand in an expression using a single pipe OR. The entire expression being this. The C OR operator does a bitwise OR operation. It takes two integer operands, treats both of them not as numbers but as bit patterns, and does a logical OR operation on each pair of bits, one from each operand. Here's an 8-bit example as drawn from the transcript. The A or B operation creates an integer with a bit pattern in which each bit is the OR of the corresponding bits in the two operands A and B. If either or both bits are 1, the result is a 1-bit. Only if both bits are 0 is the result bit a 0. So 0 in the first column, but 0, 1 in the second column gets me 1. 1 and 1 in the third gets me 1. 1 and 0 gets me 1. Here again, 0 and 0 gets me a 0. 1 and 1 gets a 1. 1 and 0. 0 and 1 both get 1s. Every bit pair ORed. The OR operator is good for setting individual bits in a value without changing any other bits. And setBit uses it to turn on the correct bit for value prime. Say, for instance, that prime is 53. Then, per the modulo rule, we'd be dealing with bit number 21 in prime set number 1. Let's assume that prime set 1 already has 1-bit values turned on for primes 37, 41, 43, and 47, as shown now in the diagram. The two operands would then be as shown here. We have the prime set element in question, the shifted 1 here, and the result of the OR down here. And that result has each pair of corresponding bits ORed together to produce a 1-bit, or to produce 1 bit of the result. The OR operation keeps the existing ones in the prime set array, even though they are matched by zeros, but it also sets the 1 bit here in position 51. And function setBit then assigns that result back into the value of prime set, the correct index of prime set, completing the task. There's also a C ampersand operator, which works exactly like the OR, except that it does an AND on each bit pair. The resulting bit is 1 only if both corresponding bits in the operands are 1, otherwise it's a 0. We'll use the AND operation in the main function a little later on. Checknum, up here, checks parameter toTest to see if it is prime by looping through all possible divisors, down here, to see if any of them divide evenly into toTest. If the loop passes through all divisors without finding an even division, then checknum adds toTest to prime set by calling setBit. And then it returns true if that happens, but false otherwise. So it returns true if the toTest value is prime. Now, there is one new concept in checknum that will show up in the assembly. It may be a familiar concept to you, but let's be sure to review it. This test here, divisor less than toTest, double ampersand, and then toTest percent divisor not equals 0. That is short-circuited. C ensures that if the first operand of a AND clause, like a divisor less than test here, if that first operand is false, then the second half is not even run. There's no point in doing so, since a false first operand ensures that the AND is false, regardless of the second operand's truth or falsity. We'll find that the assembly code jumps over the second operand of the AND clause in this case. Take a moment to be sure you understand the rest of the code in checknum. It's fairly straightforward. The loop ends either when it finds an even divisor here, or it reaches the toTest limit. And then the if statement and return value are using divisor equal toTest to in effect say no even divisors were found, or the value was prime. Now let's move on now to the main function, way up here. Main function declares relevant variables, sets all the values of prime set to 0, so all bits are initially 0, and then runs through the values 2 to 319 and passes each one to checknum to see if it is prime and to set the proper bit in prime set if the number is prime. Variable total primes counts the number of primes. Every time checknum returns true, it's incremented. By the end of this second for loop, prime set will have 1 bits for each prime value less than 320. The final for loop runs through all the elements of prime set and prints the relevant prime number for each 1 bit in prime set. And the if test that it uses needs some analysis. That's right here, prime set, bracket toTest divided by bits per int, left shift toTest percent bits per int, ampersand OX1. So I'll ask you to tear this apart with a few in-lecture questions. First, what bit will be in the LSB position in the bit pattern resulting from the shift operation? So when I do this shift, what bit from the prime set element winds up being down in the LSB position? And related questions, will we expect that bit to be a 1 or a 0, and why? Recall, as we said earlier, that the double greater than sign represents a right shift. Well, the basic answer is that the bit that gets down to the bottom LSB position is the one that represents the primeness of toTest. It'll be a 1 bit if toTest is prime. The expression first picks the prime set element containing toTest's bit, the division there, and then it shifts that element to the right by the bit number for toTest, leaving toTest's bit in the LSB spot. Here's an example, assuming toTest is 53. So we're shifting prime set 1, which contains bits for the primes from 32 to 63, including the one for 53 part way up, that guy there. And let's call that the 53 bit. The 53 bit moves down to the LSB after the shift. And question 4. We need to test to see if the 53-bit is a 1. Since integers are true-false values in C, it's tempting to just use the shifted result here as the needed test. Why can't we do that? Well, the answer is that we need a test that is true if and only if the 53-bit is a 1. Now, the shifted integer might still be true even if the 53-bit is a 0 if the other bits to the left are 1, as some of them are. So we need to knock out all the other bits aside from the LSB. We can do this via an AND operation with the value 1, which has 0 bits in all bit positions but the LSB. By the way, the hexadecimal value there is, in the hexadecimal notation, OX1 is commonly used when you want to treat a constant as a bit pattern. It wouldn't make any difference whether it's there or not, since 1 is the same pattern in decimal or hex. Now, after that AND is performed, as shown here, all bit pairs but the LSB will be 0, and the LSB will be 1 only if the 53-bit is 1. So, this is the test we need. And main uses it down here to decide whether to print toTest. So that concludes our C discussion. In the next segments, we'll look at the assembly translations of setBit, checknum, and main.